Well, in order to work with this, we need to find the eigenvalues and eigenvectors so that we can write this in its expanded form. So the first thing I want to look at is the eigenvalues. I'm always going to look for the eigenvalues the same way by looking at the determinant of A minus lambda I and setting that equal to 0. Here's my A matrix, and subtracting the lambda I matrix means we'll be subtracting lambda from the primary diagonal, which is going to make my A minus lambda I matrix 2 minus lambda, 4, 3/4, and 0 minus lambda. We take the determinant of this, I'm going to have that primary diagonal multiplied together minus my off diagonal. So I'll have 2 minus lambda times negative lambda minus 4 times 3/4. Now, if we distribute that out, I've got a positive lambda squared, a negative 2 lambda, and those 4s will cancel, leaving me with minus 3, which means this is going to factor for us. So I'm looking at lambda minus 3 times lambda plus 1, I think. Sound good? Which means we've got 2 eigenvalues, and I'll just call those lambda 1, I'll set equal to 3, and lambda 2, I'll set equal to negative 1. Now, in this problem, we are looking for the stable age distribution and to determine whether the population is increasing or decreasing. Absolute value of my largest eigenvalue, so that's going to be 3 in this case, and that's going to determine my stable age distribution, meaning if we let this iterate for a very long time, all of the vectors will tend to align with the eigenvector associated with our largest eigenvalue. So I now need to find the eigenvector that's associated with lambda of 3. And to find that eigenvector, I'm going to go back to my A minus lambda I matrix, plugging in that lambda of 3. So I'll have 2 minus 3 and 0 minus 3, so negative 3. And I know that this times my eigenvector should give me the 0 vector. And that's going back to that relationship that if AX is equal to lambda x, that's what it means to be an eigenvalue-eigenvector pair. Subtracting this over and taking care to multiply by the identity matrix so that we're subtracting things of equal size, I can rewrite that, factoring out my x vector from my A minus lambda I and setting that equal to the 0 vector. If I take this and I rewrite that as a system of equations, then that top line says negative x plus 4y is equal to 0. And when we write out the second line, we're expecting to see an equation that would form the same line. So that second row would multiply out to be 3/4 of x minus 3y is equal to 0. And if I take this second equation and I multiply by negative 4/3 and distribute that in, then I'm going to get back the top equation. So it doesn't really matter which one we work with. I'm going to choose the one with no fractions. In general, I can classify all of my eigenvectors as eigenvectors that lie along this line. And one way to write all of the possible eigenvectors is to choose one of these two to be my free variable. So, for example, if I let y be equal to t, then that would mean negative x plus 4t is equal to 0, or x is equal to 4t. So if I write that as a single vector, then I can say my x, y eigenvector would look like 4, 1 times t. So that 4 to 1 here, that's representing our stable age distribution.